In this video, I'll be going over the probability of a conjunction. And so a conjunction, and assuming independence, which I'll get to here in a few minutes, a conjunction, so the probability of A and B together is just the probability of A times the probability of B. And by the way, this P, then the stuff in parentheses is standard for probability things. And so that just means the probability of A and B, which if we just use the symbolic form, it looks like this. So the probability of A and B is just the probability of A times the probability of B. And so we have the Greens have two children. What is the probability that both are girls? So we have the probability of girl and girl. And so the probability that the first one is a girl and the probability that the second one is a girl. And so that is equal to the probability. And so G and G being girls. So the probability of the first one being a girl times the probability of the second one being a girl. And so that is 1/2 times 1/2, which is equal to 1/4. And so that is a probability of 0.25. And so if we want to look at it in the classical definition, we can build a table like this with all the different possibilities. So child 1 equal girl, child 2 equal girl, or child 1 equal boy, child 2 equal girl, or child 1 equal girl, child 2 equal boy, or child 1 equal boy and child 2 equal boy. And so then I just have highlighted here in red the one that is actual. And we see that that is just one out of these four possibilities here. And so 1/4 or 0.25. And then we could also look at it with the frequentest definition. So if you poll 1,000 two-children families, you can guess that around 250 of them will have two girls. And so that is the sort of frequentist interpretation there. So let's look at another example. So if we are rolling our 20-sided die and we roll it twice, so two trials, what is the probability that both of them are 20? And so we have the probability of 20 on the first one and 20 on the second one. And so we can just do the probability of 20 on the first times the probability of 20 on the second. And so that is 1/20 times 1/20, which is 1 in 400. So there is a 1 in 400 chance of getting a natural 20 on two different dice rolls. So we can translate this into, so the probability, so the chance of getting a 20, so that's the event we're interested in, out of the 20 possibilities in two rolls. And so that is equal to the chance of a 20 out of the 20 possibilities, which is sort of our 1 in 20. So there's a 1 in 20, so 20 down here. And then we raise it to the power of how many rolls we are doing. And so to make that a little bit more general, we have the probability of the specific event out of the possible events in the number of independent attempts. So the specific over possibilities to the power of the number of attempts here. And so what is the chance of getting 3 natural 20s? So that would be, 20, the probability of 20 and 20 and 20. So a conjunction of 3 things. And so that is this 1/20 to the third power. So 1 in 8,000. So if you, say, roll a d20 3 times, what is the chance that you'll get a 20 on all 3 of them? That would be 1 in 8,000. And so let's take a little closer look at this idea of independence. So independence just means that the chance of getting an outcome on one attempt is not influenced by any other attempts. And so having a girl as your first child does not influence the sex of the second child. And so that's what independence means with children. So if your first child is a girl, that doesn't sort of increase the chances of getting a girl or increase the chances of getting a boy on the next child. So when we're rolling our 1d20 the first time, that does not influence the 1d20 roll on the next attempt. So, if you get a natural 20 on the first roll, the chance of getting a natural 20 on the second roll is just going to still be 5%. And so it's why when playing roulette, if the last 5 spins have landed on red, we're not due for a black like a lot of people think. So I think this is called the gambler's fallacy. So the next spin will still have a 50% chance, if we're just ignoring those green ones, of being red. So if the probabilities were dependent, then one outcome would influence the other. So for instance, say the second child, so we have one child, the second child has now, instead of a 50% chance, has a 75% chance of being the same sex as the first. Then the probability of a 2-child house having 2 children with the same sex would be 1/2 times 3/4, which is 3/8, so 0.375, or if you want to think about it in percentage, it would be 37.5%, which we can see is higher than the 0.25, because now we're saying that the second child's sex has some dependence on the first child's sex, and so the probability of having 2 children of the same sex in the household would be higher. And so Steven Pinker goes through this real world case where Sally Clark in 1999 lost 2 infant sons to what is sometimes called crib death. So in the trial, a doctor testified that the probability of an affluent, non-smoking family losing 1 child to crib death was 1 in 8,500. And so losing 2 children to crib death must be 1 in 8,500 times 1 in 8,500, which is 1 in 72,250,000. So the doctor was saying that the odds of this happening sort of by accident, or without the parent, I guess, murdering the child, would be sort of extremely unlikely. And so Clark was sentenced to life imprisonment. So after the trial, critics then show that the crib death within a family are not independent. So they are not independent because there may have been a genetic predisposition, for instance, or the home itself, so the actual house may have some kind of elevated risk factors, or the parents' response to the first death may have resulted in some kind of misguided precautions. And so when it's dependent like this, we can't just do this sort of simple multiplication. I think Steven Pinker said that Sally Clark was eventually exonerated in an appeal trial. I think it was for different reasons, he said. But anyway, so the case at least has, well, I guess if you think she is not guilty, then a happy ending. If you still think she is guilty, then a sad ending. But anyway, the idea, though, is that when we have a dependence like this, we can't just multiply the odds. And that will actually get us in a future video into conditionals, and so the conditional, so what is the probability of a crib death given a genetic predisposition, but I won't get too much into that here. I'll get into that in a future video. And so in the future video, I'll give a somewhat more mathematical or rigorous sort of definition of independence. But for now, we could think of independence as, getting an outcome on one trial So on one trial, is not influenced by any of the other attempts or trials. And so that is sort of our working definition of independence. And so back up here, like I said, if we have the probability of A and B, we assume independence. So then the probability of getting a girl on the first child and a girl on the second child, given that both children are independent, that the probability of getting a boy or a girl on each one is independent, then we can do this sort of simple 1/2 times 1/2, which is equal to 1/4, which is the 0.25 probability or 25% chance. But anyway, I hope you found this video helpful, and I will see you in the next video.